Today's lesson is going to be dealing with forces and Newton's laws. A force is a push or a pull that causes an object to change its state of motion. Normally, we call this an acceleration. Forces cause things to accelerate. A change in a state of motion is an acceleration. So over here, Yoda is applying the force and accelerating the Emperor across the room. The units for force are newtons. A lot of times we are used to using pounds in America, but the SI, the metric unit for force, is a newton. When objects are falling, they're said to be in free fall. Free fall is a state of motion where things are falling without air resistance. So when we talk about objects that fall, we're always normally talking about free fall, unless, of course, we're talking about drag, which is a resistance force. In free fall, speed increases linearly with time. What that means is as something falls, it gains velocity or gains speed. And the more it falls, the further it falls, the more speed it's going to gain. We have two pictures here that show that all masses accelerate at the same rate. Both of them are in a vacuum state. The picture on the bottom left, what happens is there's a bowling ball and a feather in a giant vacuum. As they fall, you can see they fall together, and then when they hit the ground, they're hitting at the exact same time. So there's no air in that room. You know, if there's air in that room, that the feathers are going to fall much slower than the bowling ball due to the drag. And then we have actual footage from an Apollo mission where we're dropping a feather and a hammer on the moon where there's no atmosphere, and you can see the feather and the hammer fall at the same rate. So this is proof that objects without any atmosphere, without any friction, are going to all fall at the same rate. Newton was the first person to come up with this idea. Well, Galileo came up with the idea, but Newton formalized it. Newton has three laws of motion. He lived some almost 500 years ago, 450 years ago, and he was about your age when he developed calculus. He developed calculus to help him solve problems, right? He had problems, and he was like, how am I going to get this solution? So he needed a new breed of math to enable him to find this solution. And so he developed calculus. So he was in his early 20s when this took place. Newton's first law of motion is inertia. Inertia states objects at rest stay at rest, and objects in motion stay in motion until acted upon by an outside force. So we can see here two situations of inertia. The first one on the bottom left, this is Mr. Wizard. He was a scientist on TV in the 80s, and he's doing the old tablecloth trick where he has some place settings on the table. He grasps the tablecloth, pulls it very quickly, and reduces the amount of friction. So by reducing the amount of friction by pulling so quickly, what happens is the table setting stays in place because it has inertia. Inertia, objects want to stay in their state of motion. In the slow-mo video of the person falling into the net with the leaves on it, you can see the leaves have their own inertia. As soon as this person falls through the leaves and into the net, the leaves don't want to move. They're staying in their current state of motion, which is at rest. And they won't start moving until the force of gravity acts on them. So objects at rest stay at rest. Likewise, objects in motion stay in motion. So once they start moving, they're not going to stop moving until they hit something. Inertia is a resistance to change in motion. The more mass you have, the more inertia you have. So the stick man down here has much less inertia than the elephant. So as he runs towards the elephant is going to keep his state of motion because he has more inertia than the stick man does. Likewise with the train, the car and the train both have an inertia. The train has much more inertia than that van. So when the train hits the train changes the van's inertia easier than the van changes the train's inertia. And this is why when you drop a ball out of the window, the ball and the earth have equal amount of force on each other, but the ball falls to the earth because it has much less inertia than the earth has. Newton's second law of motion says a net force causes an acceleration. F net equals ma. That's the formula for Newton's second law. A net force is the total amount of force. So the total amount of force acting on a system is what's going to cause a system to accelerate. If we look at this car, we can see the top example, if our acceleration is to the left, we would take our two forces, the engine force and the friction force, and we would combine them. If the acceleration is to the left, what that's telling me is that the engine force is greater than the friction force. If the acceleration is to the right, we would be braking. This would tell me that friction is greater than the engine. The net force tells me that friction is greater than the engine and the object is braking. And then finally, if the acceleration is zero, this is what we call a state of equilibrium. Anytime an acceleration is equal to zero, we're in an equilibrium state. So in this case, our engine force and our friction force would be equal to each other. In the vertical, the normal force, which is the force of the ground on the car, and the weight, they're normally in an equilibrium state, and the acceleration in the y is equal to zero. Your car is not usually accelerating upward or downward unless it's going over a bump or sinking or falling off a cliff. Weight and mass, these are two terms that we get confused a lot. Mass is actually a measurement of your inertia. The amount of mass you have is going to determine your amount of inertia. So the more mass, the more inertia, the harder it is to change your state of motion. Weight is gravity's effect on a mass. So the acceleration of gravity is 9.8 meters per second on Earth. It's about 1.67 meters per second on the moon. So it's about 6 times less on the moon than it is on Earth. When we go to find our weight, we use Newton's second law. Weight equals mg. It takes your mass in kilograms times gravity to give us your weight. So if you were to go to the moon, you can see your mass does not change. You still have the same mass on the moon that you do on Earth. What changes is your weight, and this is because the acceleration due to gravity is much less on the moon, because the moon is smaller. Pounds and newtons. Pounds we use in the English system, newtons we use in the metric or the SI system, and kilograms is a measurement of mass. And Newton's final law, the third law of motion, is known as action-reaction. The force of A exerted on B is going to be equal in magnitude and opposite in direction. So when you push on something, it pushes on you with the same amount of force. And the picture of the finger on the wall, if you put your finger and you place it on the wall, you push on the wall, the harder you push your finger, the harder the wall is going to push back. And you can see over here with our woman with her gun, the recoil of the gun, right? The gun is putting a force on the bullet is putting the same amount of force back on the gun, which is what causes the gun to kick backwards. That's an equal and opposite amount of force. So anytime you apply a force, that force is applied back to you in the same amount. That's Newton's third law.